Implicit differentiation is a hard topic, so let's do another example. Let's work through this problem right here. It says, find the slope of the tangent line to this curve with this equation. It's a cubic equation. X cubed is cubic. 5x squared times y is actually also cubic because you add the exponents, even though you don't combine the x and the y. Quadratic term there, 2y squared equals 4y plus 11 at the point 1, 2. Let's go ahead and do what we're told to do here, but let's also think about this in terms of other things that we've learned, like multivariable calculus. I'll write the equation first. X cubed plus 5x squared y plus 2y squared equals 4y plus 11. And the point in question, again, is the point with coordinates 1, 2. All right, that is our equation and point. We want to find the slope of the curve at this point if it exists. When you do implicit differentiation, you assume that this equation defines y as a function of x near this point. Effectively, you assume that near that point, the graph passes the vertical line test and only goes through it once. Now, overall, the graph might not pass the vertical line test. It's possible that if you graph the entire curve defined by this equation, that it doesn't pass the vertical line test. But we're hoping near this point it does. So we make that assumption. Assume y is a function of x. Could we solve for y as a function of x? Actually, we could here. It wouldn't be too bad. Because this equation is quadratic in y, we could subtract 4y and subtract 11 from both sides and actually use the quadratic formula to solve for y as a function of x. But we actually don't have to do that. That's kind of nice, actually, with implicit differentiation. Assume y is a function of x and differentiate with respect to x. That assumption that y is a function of x is essential for understanding what you're doing here. If you don't make that assumption or don't realize you're making that assumption, you don't really understand conceptually what's going on. X cubed is certainly a function of x. Differentiate it with respect to x, I get 3x squared. But with the 5x squared times y, that's the product of two functions of x. Why? Because I'm assuming y is a function of x. I need the product rule, and hopefully I won't make a mistake this time. I've got a left function, 5x squared, and a right function, y. Can I write y equals f of x? I could. Remember I showed you that last time? We did it with an f of x in there first. But it's not traditional to bother with that. Just remember y is a function of x. Left, 5x squared, d right, what's the derivative of y with respect to x? Not 0. This is not partial derivatives here. I'm assuming y is a function of x, so the derivative of y with respect to x is dy dx. Left d right plus right y, d left, the derivative of 5x squared is 10x. So that's right d left. With the next term, 2y squared, I need the chain rule. The derivative with respect to x is not 0. It's not 4y. It's 4y times dy dx. If I had an f of x there instead of a y, 2 times f of x quantity squared, I get a 4 times f of x times f prime of x. And again, there's nothing wrong with doing it that way. It's just not traditional. On the right side, I differentiate with respect to x, keeping in mind y is a function of x, so I get 4 dy dx. 11 truly is a constant. It differentiates to 0. Now, solve for the unknown that you want to find, dy dx. Even though it's a complicated looking equation, it is linear in the unknown quantity dy dx. I can solve for dy dx by isolating it. First, on the left, factor it out of the 5x squared and the 4y, and I'm also going to imagine subtracting 4 dy dx from both sides, so I'll also get a minus 4. Because I subtracted 4 dy dx from both sides before factoring it out in my mind. On the other side, bring everything else. Minus 3x squared gets added to both sides, which is the same as subtracting 3x squared from both sides. Also subtract 10xy and get this. Now divide both sides by what dy dx is being multiplied by. To get dy dx is negative 3x squared minus 10xy all over 5x squared plus 4y minus 4. And with what happened last Friday, I feel like I want to make sure I check my work here. So I did my checking last Friday in Mathematica. I'll do it in Mathematica again today. Got the code from last Friday. I'll make appropriate modifications here. Before I can use the code, well, or one thing I'd like to do before I use the code is I'd like to take this equation and rewrite it right at the start by subtracting 4y and subtracting 11 from both sides. This is equivalent to x cubed plus 5x squared y plus 2y squared minus 4y minus 11 equals 0. And this is going to be my function that I plug into Mathematica for f of xy. So I'll type that now. X cubed plus 5x squared times y plus 2y squared minus 4y minus 11. The 0.12 is on the graph of this, is on the graph of this equation. It is a place where this function equals 0. If I replace x with 1 and y with 2, hopefully I get 0 here. Yes, I do. But now let me check my implicit differentiation in the following way. I'm going to go ahead and use the built-in d command. D means differentiate. The equation f of x comma y equals 0. I do want to use double equal signs here because I'm not wanting to set this equal to anything. I'm trying to work with equation that I'm ultimately going to solve. And so that's a case where you need double equal signs in Mathematica. That using single equal signs in this kind of context is part of what gets people into trouble with Mathematica's memory. I'm differentiating with respect to x. Oh, one other thing that I need to do here for Mathematica's sake is to emphasize to Mathematica that y is a function of x. So I'm actually typing y of x in there. That will tell Mathematica, hey, assuming y is a function of x. If I differentiate both sides of the equation, let's double check that I did it right here by hand. Compare what you see here with what I did here. You see a 3x squared in both places. You see a 10x y. That's Mathematica's writing as y of x because that's how I typed it. Also a 5x squared dy dx. That matches this. Mathematica's writing as y prime of x. A 4y times y prime. That matches this. And a minus 4y prime. That's matching taking the 4 dy dx and subtracting it from both sides. Equaling 0. I'd like to now solve that equation algebraically for y prime of x. So I'm going to copy and paste that equation into here, put a comma, and then y prime of x is telling Mathematica what to solve for. Compare that answer with this answer. Up top, you see a negative 3x squared minus 10xy of x. I just write a y. On the bottom, you see a minus 4 plus 5x squared plus 4y. Yes, this is correct. I did it right. Now I'm going to plug the point dy dx equals, well, x equals 1, y equals 2 into that to get the slope. Replace all the x's with 1 and replace the y with 2. Negative 3 times 1 squared minus 10 times 1 times 2 over 5 times 1 squared plus 4 times 2 minus 4. That gives me, looks like negative 3 minus 20 on the top, negative 23. On the bottom, it looks like I get 5 plus 8 is 13, minus 4 is 9. Looks like the slope is negative 23/9. How can I double check that with Mathematica? Well, I could have Mathematica compute the fraction. I can also take the preceding output. The percent sign here refers to the preceding output. Using a slash and a dot is going to allow me to ultimately replace x in that preceding output with 1 and y of x in that preceding output with 2. The percent sign refers to the preceding output, slash dot, and this stuff then allows me to plug those numbers into that preceding output. Negative 23/9. There we go. Do you need to remember this for the test? No. You should know how to use D for the exam. Might test you have a little bit of Mathematica. You should know how to use solve. Those kinds of things for the exam. You don't have to know this syntax. But I'm checking my work, making sure it's right. Now let's use this to come up with a tangent line approximation. We were not asked for that, but we could certainly do it. So another one of our main topics for today is review tangent line approximations. Y is going to be approximately, for this curve, the y value in x is 2. Maybe I should call y as a function of x here. Let's give it another name. Let's call it g of x, just for the sake of simplicity and to distinguish it from f, unlike what happened last Friday. Y is going to be g of 1 plus g prime of 1 times x minus 1. That's using the linear approximation formula in section 3.9 with the a equal to 1. Why 1? Because that's the x coordinate of the point I'm interested in. That's why. I'm focused on this point still. 1, 2. G of x is y is an unknown function of x. I never found the formula for g, but that's okay. I don't need it. Because I've got a value, g of 1 is 2. And I've got a derivative, g prime of 1 is negative 23/9. So this becomes 2 plus 23/9 times x minus 1. This is approximately g of x when x is close to 1. Where again, g of x is this unknown function. I never solved for it. But I do know its value at 1, and I do know its derivative at 1. And therefore, I could estimate g when x is close to 1. For example, g of 1.1 should be approximately 2 plus 23/9 times 1.1 minus 1. 1.1 minus 1 is 0.1. 23/9 is about, well, it's 2.5 repeating times 0.1. Add 2, I get about 2.256, say. Let's round to that. This is about 2.256. i.e., in other words, the point 1.1 comma 2.256 is approximately on the curve where f of x, y equals 0. We know the point 1, 2 is for sure on the curve. There's an approximate point on the curve. Let's see if it seems right with a graph. I'll make my contour plot. And actually, if I'm not trying to plot the whole function, I just want to plot the equation f of x, y equals 0. Here's the syntax. This is going to be some curve in the plane. There it is. Oh, look, it doesn't pass the vertical line test. Yeah, these curves don't necessarily pass the vertical line test. That should make some intuitive sense. Like if we tried to solve this equation for y as a function of x, it's quadratic. You'd have to use the quadratic formula. You get a plus or minus. You get 2 functions of x. Only one of these curves goes to the point 1, 2. this one on top, the 0.12 is right around, well, right around here. Let's actually plot the 0.12 as well in the same picture. Don't worry about my syntax here. I am just trying to plot the 0.12 in the picture as fast as I can and make it fairly big. There it is. There's the 0.12. Make it even bigger. It is on the curve. Where's the point? 1.1, 2.256. Hopefully close to being on the curve. 1.1. Oh boy, I must have made a mistake. Oh, I did make a mistake. It's a minus sign there, sorry. Can't avoid mistakes here, it seems. Minus sign. Minus sign. Not 2.256. 23/9 times 0.1 gets subtracted from 2, sorry. 1.744. 1.744. This delays it getting uploaded because I have to make the annotations correcting what happened. 1.744, 1 comma 1.744. Let's see if it's close to being on the curve. 1 comma 1.744. Yeah, not exactly, but close. Oh, did it freeze again? Oh, there we go. Okay. Not exactly, but close. That doesn't seem right either. What in the world's going on here, though? Oh, I forgot my 1.1. That's even closer. Okay. You can't even tell it's not on the curve. I could also plot the tangent line to the 0.12 in here as well. An ordinary plot. Tangent line equation is 2 minus 23/9 times x minus 1. X going between, say, 0 and 2 to keep a small range here, and I'll make it red. Oh, and it changed the window here on me. Sometimes that happens. That can be fixed. Okay, there we go. That's the tangent line to the curve at this 0.12. And we use that to approximate the other point. But it only works near that point, right? You can see as you get further away from x equals 1, the tangent line approximation is not doing so hot anymore. That's because the curve's a curve. It's not a straight line. It is locally linear. When you zoom in near this point, it looks more and more like a straight line. If I make a contour plot of this level curve of this function near the point in question, like x going from 0.9 to 1.1 and y going from 1.9 to 2.1, it will look pretty straight. Looks like a straight line, for all you can tell, but it's not, it's a curve. But oftentimes curves are locally linear. If you zoom in near a point, it's going to look more and more like a straight line. Not all curves, though, are that way. The absolute value function, remember, it's not differentiable at the origin. The closer you zoom in near the origin, it still looks like a V with a corner. As long as the scale, the rate at which you approach the origin is the same in the x and y directions, that'll always be the case. That's not locally linear at that point.